I will deal with something that I started last year. Last year it was an idea, and now I'll present formulas. So, the main idea, some martingales on Sobolev groups of diffeomorphism of flat and dimensional torus are describe motion of some viscous fluid with some additional properties. And those martingales satisfy a system of two equations with so-called mean derivatives. And those martingales that satisfy these equations will describe solutions of Burger's equations with additional properties. So first of all, I'll describe what is mean derivatives. The equations are with mean derivatives. Then something about those Sobolev groups of diffeomorphisms, and only after that those two equations, and what sort of Burger's equation we obtain. So the main idea, it is some generalizations of approach introduced by Eben and Marston in 1970 of Lagrangian approach to hydrodynamics, where they produced a brilliant description of ideal fluids. But when they came to viscous fluids, it was not so brilliant and not so geometrical. But we have found that if we replace their covariant derivatives on those groups by the so-called backward mean derivatives, then we obtain very close to that for ideal fluids to viscous. And so what about mean derivatives? Mean derivatives were introduced by Edward Nelson in his paper of 1966. He published a new sort of quantum mechanics, called him stochastic mechanics. But after that, it turns out that such equations arise in many other problems of mathematical physics. So we have probability space, consider a process on this space that is L1 at any time t, and introduce yes, we use the notion of conditional expectation by n xi at moment t. We denote the sigma algebra that is generated by pre-images of Borel sets on that flat torus. And this is the definition of forward mean derivative. You see, it's ordinary derivative, but here is conditional expectation with respect to the present. Sigma algebra, letter n means not present but now, because the past has the same initial letter. Yes, now this is backward mean derivative. The half sum is called symmetric mean derivative, you see. And the derivative of a process is called current velocity. There is osmotic velocity also, but it's half difference. But we shall not consider them in this talk. Yes, we will mainly work with backward and symmetric mean derivatives. And some properties. First of all, it's idea of Partha-Therati that any conditional expectation can be described as composition of some Borel measurable vector field in which we institute the process. Yes, and yes, 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 yes. If it is not Markovian, then there are several differences with respect to which. Yes, our examples will be Markovian. Yes, and this vector field is called regression. I will use this term. Then backward mean derivatives of a vector field along a process. You see, the same idea with conditional expectation. Yes, then the second mean derivative. Yes, this is the regression of backward mean derivative, and it has the following form. It's formula by Nelson. Yes, where nabla, as usual, and delta is Laplacian. Second derivative. We apply a formula for derivative of regression along the process and obtain the following formula for a process with unit sigma multiplied by unit diffusion coefficient. For more complicated processes, there is such a situation. If it is not a unit, then we suppose that it's convertible. And after convertation, we obtain a new Riemannian metric on this torus. And with respect to this Riemannian metric, we obtain divergence, gradient, and all other operators of vector analysis. And we shall denote them with capital first letters. Now, this is the formula for current velocity. Rho is the density of our process, and for any bounded continuous function f, this you see its expectation, and its integral on. I shall say it from the very beginning. Everything we consider on finite time interval, from 0 to t capital. Yes, and this is the description of this expectation through the density. And then this density with the current velocity satisfies this equation. We see its divergence with respect to that new Riemannian metric. Yes, and it looks very close to equation of continuity. And if the diffusion coefficient depends on t, then we obtain the same formula where here would it divergence will be divergence on level surface with that constant t. Now, groups of diffeomorphisms. We n-dimensional, flat n-dimensional torus. This means that its metric is inherited from Rn before obtaining a quotient space. And we consider Sobolev diffeomorphisms of class HS, where H is greater than n over 2 plus 1. This means that everything is CID in one differentiable functions. It's a group. It's a Hilbert manifold, and a unit here is this is the identity, and the tangent space at unit is the space of all HS vector fields on this torus. Below, we shall consider the case where S is greater n over 2 plus 2. Yes, this is scalar product in tangent spaces. It's so-called weak Riemannian metric. And since it's a group, we can consider right invariant and left invariant vector fields. Right shift is smooth, and left shift, unfortunately, is only continuous. Now, remember, recall that the tangent bundle of the torus is trivial. It's a direct product of torus and Rn. And we introduce several operators. B, it's a direct product, and its projection on the second multiplier. A is inverse to B, but it sends Rn into the tangent space at M. And so having a vector X in basic Rn, we at the time obtain vector field on the torus, where at every point there is the same X. Yes, and now Q is superposition first B and then A, G at M. We obtain translated vector field from unit to diffeomorphism at G. I think it's not interesting. It's a definition of a geodesic curve, the same as usual. But from that A, we obtain a right invariant operator field by this formula. And after that, we obtain a vector field on the group, where X is from Rn. And every right invariant vector field, this is smooth. Now, exponential mapping. Exponential mapping on flat torus is trivial. We add the same X to any point of the torus. And after that, we apply to this exponential, we obtain right invariant mapping exp with bar. Yes, and then we apply x with bar to this vector field. That is m plus x. So exponential mapping, we add x the same to any point of the torus, and then obtain Polution space. Good. Yes. Now we need Wiener process on this group, and this Wiener process with coefficient sigma positive constant is described by this formula. And it is martingale as well as W, this W on the torus. Yes, and for a given omega small from omega capital in our probability space, and given t, W of t at omega is a constant vector, is Rn. And this means that for a given omega and t, the action, I didn't say about this operator, but it's smooth and translate geodesics into geodesics. Another martingale. Instead of W, we take stochastic integral of some non-random operator dependent of time and integral eta. It is also martingale, and its action is described by this formula. To any m, we add this integral. Yes, I'm very close to that. Yes. No, and so we can show those two equations. Yes. The equations are as follows. The first one is a second mean derivative, backward mean derivative of x is equals some right invariant vector field, meaning its external force. So we at unit we obtain real external force that acted on the torus, and the second it's equality of backward mean derivative equals two symmetric mean derivatives. And why martingales? Because if you remember the formula for symmetric mean derivatives, it's half sum forward and backward. And from this formula, we see that the forward mean derivative equals 0. And if it equals 0, then the process is a martingale. Yes, another, I missed the formula about backward mean derivatives. Let me say it orally. Backward mean derivative of W of t of Wiener process is W of t divided by t. And for symmetric mean derivative divided by 2t. Because first forward derivative is 0, yes. And second backward mean derivative of w over t is 0. Now we will consider these two equations for those two martingales that I introduced. First, it is W sigma. And the right-hand side should be constructed from finite dimensional derivatives. And for this case, its second mean derivative is 0, as I have told. And second, this one. Then, from formulas for backward mean derivatives in the very beginning, we obtained that the first is the left-hand side of this equation. We translate everything to unit and obtain in tangent space, the space of HS vector fields, equation. Left-hand side of this equation is left-hand side of Berger's equation. It follows from formulas for second backward mean derivatives. And as I told right now, the right-hand side is 0. So it's Berger's equation with 0 external false. And this is the equation that we found for symmetric mean derivatives. It is analogous to continuity equation. So this martingale describes a solution of Berger's equation. It's viscous fluid with some viscosity sigma square over 2. And please note, it exists. It is constructed from Wiener processes that exists. And also, it satisfies this analog of continuity equation. The second martingale, by all formulas for conditional expectations, we obtain that second backward mean derivative of this process is derivative of b multiplied with w of t over t. Please note it doesn't exist at t equal to 0. But if we start from some time instant greater than 0, then it's okay. And for this, we introduce by G bar the right invariant vector field on the Sobolev group of diffeomorphisms. And the second is the same. Then we obtain solution equation of this sort. But this regression will be denoted like this. And this is the second order differential operator that is not Laplacian. It is constructed from diffusion coefficient. And so we obtain this left side of the equation that we are instead of ordinary Berger's, but the right-hand side is this B. And so the first equation is like this, The second equation is like this. Here we have to include divergence that on level surfaces. Nevertheless, it is again an analog of continuity equation. And please note that this solution exists. It is constructed from the process that exists. And some words about what to do with zero point, zero time. We can introduce new auxiliary function, called it t sub 0 of t, that equals t when t is greater than t sub 0, and t sub 0 if it is less. Then for t started at t sub 0, everything is okay. But if we consider two different points, t01 and t02, so from the greater of them, they coincide. And so we really obtain some models of viscous fluids that exist since they are constructed from finite dimensional processes, Markov processes, that do exist. Thank you.